In this video, I introduce WaveGrad conditional diffusion models for waveform generation. Starting square function sy is defined as a gradient of log density at the data point y, as shown here. A sample y tilde from the density by is computed by using longevity dynamics, as shown here, where h is a sample size. Zi sampled from a normal distribution, and S is a stochastic gradient descent in the data space. The denoising score matching objective is defined as here, where P is the data distribution and Q is the noise distribution. Denoising score matching models rely on noise distribution to provide support for learning gradient of the data log density. WaveGrad is a conditional generative model of waveform samples, which uses the denoising diffusion models to generate the noise distribution that is used to learn the square function. WaveGrad model P theta computes a conditional distribution which is written as a margin over the latent variables from y1 to yn, as shown here. The diffusion forward process posterior Q is defined as a Markov chain, as shown here, where each iteration has a Gaussian noise Q and some noise schedule from beta 1 to beta n. Diffusion process Yn can be computed for any step n in a closed form, as shown here, where E is sampled from a normal distribution alpha 1 is equal to 1 minus beta n, and alpha n bar is a product of alpha s. The gradient of this noise distribution is calculated from this formulation, where E is a noise distribution. By reparameterizing Yn to E theta, the denoising square matching objective is written as here, where Cn is function of the diffusion schedule beta n. WaveGrad reparameterizes the model to condition on the continuous noise level alpha bar instead of the discrete iteration index n. Setting Cn is 1, the square matching loss becomes this formulation. Here is a training process of the WaveGrad model. Diffusion models sample n from a uniform distribution and then compute alpha n. WaveGrad is required to draw noise schedule root alpha bar and the diffusion steps n. For continuous noise level, WaveGrad directly samples alpha bar by using the hierarchical sampling strategy, namely first samples S from a uniform distribution for a segment between LS-1 and LS, and then compute root alpha bar by sampling the segment uniformly. Use this hierarchical strategy, WaveGrad only needs to be trained once, yet inference can be run over a larger space of trajectory without the need to be retrained. Here is the sampling process of the model. Here, this is the WaveGrad architecture. This is the 5 upsampling blocks. This 4 downsampling blocks. 2 convolution layers above the upsampling blocks and below upsampling blocks. This is a feature-wise linear modulation. And this convolution layer before the downsampling blocks. WaveGrad input consists of the mirror spectrogram conditioning signal X, as shown here, a noise wave generated from the previous Yn and the noise level root alpha bar. The WaveGrad model produces En, as shown here, at each iteration, which indicates the direction to update Yn. Each upsampling block includes two residual blocks, as shown here, as one residual block, the second residual block. And each downsampling block includes one residual block, as shown here. The feature-wise linear modulation combines information from both noise waveform and the input mirror spectrum root alpha bar, as shown here. FILM produces the scale gamma and bias xi, which are used to construct the input to next stage, as shown here. Where D is output from the downsampling block, U is output from the upsampling block, and this sign is a head mode product. For more details, please check with these references. Thank you. Bye.